Since the properties of elements are to a large part determined by their electron configurations, and since the periodic table is based on those electron configurations, we do see some predictable trends in the periodic table. The first one that we're going to talk about, a very important one, is the number of valence electrons. So these are the electrons in the outermost shell, and so they are the ones that play the greatest role in the chemical properties of the elements. So these first elements over here, this first group, they are starting a new shell. So they are putting their first electron into their outermost shell. They have one valence electron. And then we continue with the second family, group 2, having 2 valence electrons. These transition metals are adding to the D level, but it's one level down. So if these two elements here are adding one electron to the level 4s, the second one to the level 4s, these ones are not in general adding any electrons to level 4. They're back in level 3. There are some exceptions within the transition metal area to the order in which the electrons are filling, but for the most part these elements still have 2 electrons in their outermost valence shell. And then over here we start filling up more electrons in level 4 again, with the first electron being added to 4p. This is the third valence electron. Then we have the 4th, 5th, 6th, 7th, and 8th. We talked about how the noble gases have a full outer shell with 8 electrons. There is an exception for helium. It's too small. It only has 2 valence electrons, but the rest of the noble gases have 8 valence electrons. Going down the periodic table, this 4th period is filling the 4th shell, then the 5th shell, then the 6th shell. So as you go down the periodic table, you have increasing size, sometimes referred to as the radius of the atom or ion. We have the increasing size going down the table. Going across the table from left to right, we're in the same level, filling up pretty much the same level, but the number of protons in the nucleus is increasing. And so that positive charge in the nucleus is pulling on those electrons, shrinking that cloud of electrons, making the atom smaller. So going from left to right across the periodic table, atoms are getting smaller. So they're increasing in size going from right to left, which seems a little bit unusual, but the increasing size is going right to left and then down. We have some other properties that increase as the element gets smaller. So they are the opposite of this increasing size trend. So they increase going up and to the right. One of these properties is the first ionization energy. This is the energy needed to remove an electron from the element. If you want to think about it in a relatively simple fashion, if you have a small element, the electrons are fairly close to the positive charge in the nucleus that's attracting them, so it's going to be harder to pull them away than it would be for a larger element where the electrons are further out, maybe easier to remove. Then in contrast to the first ionization energy, which is how much energy it takes to remove an electron, how difficult it is to remove an electron, metallic character would be a characterization of how easy it is to remove an electron. Metals usually form cations fairly easily, and they do so more easily going to the left and down the periodic table. Another property that generally increases going to the left and down the periodic table is the energy associated with adding an electron to an element. For the smaller atoms, just in general, it is easier to add an additional electron to something that's so close to a positively charged nucleus. This particular property, though, has a lot of different exceptions and nuances that we're going to have to look at more closely. So we will look at all of these properties more closely, actually. So ionization energies increase going up and to the right, because it is more difficult to remove an electron from a smaller atom, and this is the opposite of the size trend. There are a couple of exceptions, especially in the first 3 periods of the periodic table. It's not as smooth going an increase from left to right. So instead of a smooth arrow increasing from left to right, Let's go ahead and draw one like this with a couple of dips. So going across the periodic table, there's a dip in group 16. So oxygen and sulfur are in group 16. So going from group 15 to group 16 across the periodic table, instead of seeing an increase, you see a dip in the energy needed. There's also a decrease in going from group 2 to group 13, because it's easier to remove a p electron than an s electron. So again, this is mostly in the first 3 periods of the table. These exceptions disappear as you get further and further down the table, but especially in these first 3 periods. Let's take a look at the dip going from group 2 to group 13. And as our examples, we'll use beryllium and boron. Beryllium is in group 2, boron is in group 13. If there were no exceptions, then it should be more difficult to remove an electron from boron, because it should be increasing going across the periodic table. But we find that it's easier instead to move an electron from boron than it is from beryllium. And this makes sense looking more closely at the orbital diagrams here. The electron that you have to remove from boron is a p electron, and it's all alone, and it's a little bit further from the nucleus than the s electrons. So that one is a little bit easier to pick on than for beryllium, where you would have to pick on one of these 2s electrons, which is paired and full. We've got a full orbital here, got a pair of electron. We don't have an electrons all alone. And so it's a little bit tougher to get at this 2s electron than it is to get at this 2p electron and remove it. So that's why we see this dip. It's a little bit easier to get that electron away from boron than you would expect. Now let's look a little bit at the dip going from group 15 to group 16. And as our examples, let's pick nitrogen and oxygen and look at their orbital diagrams. Nitrogen has 7 electrons, 1s2, 2s2, 2p3. So it has this half-filled p orbital. And that is an extra favorable situation. So it's kind of nice to have a full orbital, but it's also nice to have a half-full orbital. It just kind of gives a little symmetry. We have 1 electron in each of these possible boxes. So this is just a little bit extra favorable situation. Oxygen has a 4th electron in the 2p orbital, so it does not have a half-full p orbital. So again, if there were no exceptions, the ionization energy would increase going across the periodic table, and we would expect it to be more difficult to remove an electron from oxygen. Instead, we see this downturn, we see a dip, so it's actually easier to remove an electron from oxygen. So why would that be? Well, removing this electron from oxygen creates a 2p with 3 electrons in it. It creates this extra favorable half-filled p orbital. So removing this electron creates a favorable situation. On the other hand, for nitrogen, removing an electron disrupts a favorable situation. So it's tougher to remove that electron from nitrogen than it is to remove it from oxygen. That's why oxygen shows a slight decrease in the energy needed to take the electron away. All right, let's take a look at some of the ionization energies. Your textbook actually shows these values of the first ionization energies of a few elements, most of the elements, it seems like. And we can see this general trend that these ionization energies are increasing, going up a family for, let's say, this family over here, going up this column. These numbers are all increasing. Going up this column as well, you pick a column and you go up and you see that the numbers are increasing as you go up that column. Going left to right, in general, you see an increase. So you see a general increase going from left to right across the periodic table. That one is not as smooth. There are a few dips, especially in these upper periods of the periodic table. So we mentioned this dip going from group 2 to group 13. Instead of going up, going across the periodic table, left to right, we see boron going down. It's less than beryllium. Same thing with magnesium and aluminum. And even with calcium and gallium, we see it slightly. By the time we get to strontium and indium, it is still going up for those two families. So here's where our exceptions are in these upper periods of the periodic table. So we also mentioned a dip going from group 15 to group 16. So boron to carbon, we're getting larger. Carbon to nitrogen, we're getting larger. But then nitrogen to oxygen, we do go down a little bit before we increase again for fluorine and for neon. We do see a dip going from nitrogen to oxygen rather than the increase that we had been seeing and that we see again afterwards. And phosphorus to sulfur, again we see a dip rather than a continuous increase, and we even see one from arsenic and selenium. But by the time we get down to antimony and tellurium, we still see an increase. There's no more dip and exception to see. So these exceptions are in the upper level of the periodic table. Instead of just removing one electron, so the first ionization energy is the energy required to remove an electron, you can try removing more than one electron. If you try to remove a second electron, that would be the second ionization energy. Then if you remove a third electron, that would be the third ionization energy. And those get harder and harder. The second ionization energy is higher than the first ionization energy. The third is higher than the second, and so on. So going from IE1, to IE, let's say 5 or 6, removing more and more electrons is going to get tougher and tougher and tougher. So these are getting higher and higher and higher. However, they don't get higher in a smooth fashion. There is a jump. When you run out of valence electrons and you have to dip into those inner core electrons, you get a jump in energy. So once you've hit the last valence electron and you have to jump to the core electrons, you see this jump in energy. So there is a table that looks at this in your textbook. I have one that I put together in one of my discussion worksheets that I'll take a look at now. Let's take a look at a table of some ionization energies. So these are not just the first ionization energies. IE1 is the first ionization energy to remove the first electron from an element, from an atom. And then if you want to remove a second electron, that would be the second ionization energy, and the third, and the fourth, and the fifth, and the sixth. Now we have like a +6 cation, and we're removing a seventh. So as you might expect, it's getting more and more difficult. It's taking more and more energy to do that because you're removing electrons from something that's already positively charged and is very attracted to electrons. So it's increasing in energy going across from the first to the seventh ionization energy, but it's not increasing evenly like that. Instead, it's increasing, and then at some point there's a jump, and that happens when you've run out of valence electrons. So this would be the last valence electron, and this would be the first core electron. So when you've run out of that outermost shell, those valence electrons, and you have to dig deep into some of the inner electrons, that's going to take more energy because they are closer to the positively charged nucleus and it's harder to get them off of there. So let's take a look at these numbers. They all start in the high hundreds and they all go into the 20,000 range. So if you'll notice this first row and this last row, they kind of go from the teens of thousands into the 20,000. Whereas this one here, it goes from only about 8,000 to 27,000. So this is more than triple. This is rather a big jump in energy. So this is where the big jump is for this element. It's been sort of increasing little by 1,000 or 2,000 each time, and then all of a sudden it triples in energy. So this is definitely a very big jump, going from the 6th electron to the 7th electron. As I mentioned, these ones, the big jump is not at this spot. This one over here, it seems like there is kind of a big jump over here. We're more than quadrupling the amount of energy going from the second to the third electron. So that's where the big jump seems to be in this element over here. Whereas in this element over here, it seems to be fairly smooth all along after this first jump. This first jump is really like 9 times as much to remove the second electron as it was to remove the first electron. So this one, it seems like the big jump in energy happens here from the first to the second electron. So now that we've found the jumps, we know where the last valence electron is. So for element X, it had 2 valence electrons, and then that third electron was when it had to dig deep. So we have 2 valence here. For this one, it looks like we had 6 valence electrons, and the 7th electron was the one that got really difficult. And for this element, it seems like it only has 1 valence electron, and then the second electron right away is difficult. And then from this worksheet, trying to figure out which one would match with magnesium. We know magnesium is an alkaline earth metal. It has 2 valence electrons, so element X would most likely be an element in that group like magnesium. All right, let's try circling the element in each pair with the higher first ionization energy. So remember, the first ionization energy increases going up the periodic table and generally increases going towards the right. Especially in those upper periods of the periodic table, there is a little bit of a dip. Going from 2 to 13, it decreases instead of increasing. And also going from 15 to 16, we have a little bit of a dip, an exception there. So potassium versus sodium, those are both in group 1. Potassium is larger than sodium. This is how it looks on the periodic table. And so the higher first ionization energy would be sodium because it increases going up the table. So at the very end of the periodic table, we find bromine and krypton. This is the last 2 groups, 17 and 18, so not the groups involved in these dips over here. And so in general, it's going to be higher going to the right. Magnesium versus aluminum. This is one of those exceptions. Aluminum is to the right on the periodic table, but this is where one of those dips is. So magnesium would have a higher first ionization energy. Boron and aluminum are above and below each other on the periodic table. So the boron is higher on the periodic table. That would have a higher ionization energy. For silicon and phosphorus, this is not one of the exceptions where we see a dip. So in general, we see increasing ionization energy going from left to right. So phosphorus would have a higher first ionization energy. And between nitrogen and oxygen, this is one of those exceptions where we see a dip. So normally we would expect the element on the right to have a higher ionization energy, but in this case, nitrogen does. It goes down, going from nitrogen to oxygen. So the ionization energy where you would see a jump, since aluminum has 3 valence electrons, it would be extra difficult to remove the 4th one. So we would see an extra high amount of energy needed for that 4th ionization energy. Rubidium has 1 valence electron, so we would see extra difficulty when we try to remove that 2nd electron in the 2nd ionization energy. And magnesium has 2 valence electrons, so we would see extra difficulty when we try to remove that 3rd electron, the 3rd ionization energy. The trend in electron affinity compared to ionization energy is definitely more confusing. So ionization energy, remember, it increased going up and to the right, but we had a few dips going left to right, so there were a couple of exceptions that we had to worry about. For electron affinity, adding an electron is in general the opposite, increasing going down and going to the left, but there are a lot more exceptions. It's almost easier to focus on what the exceptions are, what the different trends are that you see in the periodic table. So one of the first things that makes it difficult to relate to is that some of the numbers are negative numbers. So when you look at the chart, some of the numbers seem larger, but they're a larger negative number. Whereas with ionization energy, they were all positive numbers. It always takes energy to rip an electron away. It's just that it might take more energy or it might take less energy. For the electron affinity, sometimes it costs energy to add an electron. Sometimes it's a good thing to add an electron and you get energy out and it's exothermic. So that right off the bat makes it a little bit difficult to judge what these numbers are. So instead, let's focus on the specific cases that we see in the periodic table. So the noble gases we have mentioned already have the perfect electron structure. They already have a full outer shell They really don't want another electron. Whereas halogens in group 17, so we're talking about group 18 versus 17, these guys are all set, and these guys want an electron to get like these guys. So adding an electron to a halogen is really, really easy. They want another electron. Noble gases do not want another electron. So it's much more difficult to add an electron to a noble gas than to a halogen. You'll see in the table the halogens have these large negative numbers. You get a lot of energy out of adding an electron to the halogen. It was a good thing. Whereas there are high positive numbers in general for the noble gases. So it costs energy to do that. Something that is more surprising to me is how difficult it is to add an electron to an alkaline earth metal. So let's compare sodium and magnesium. We have an alkaline metal in sodium, alkaline earth metal in magnesium. So when you add an electron to sodium, it is going to go here into this s orbital because the 3s only has one electron, so you're going to put an electron in here and fill up the 3s orbital. Magnesium, the next one over, so we have 11 and 12 electrons in these elements. So the 12 electrons of magnesium mean that the 3s orbital is already full. So when you add an electron, it's going to go into the 3p orbital. So that's where that electron is going to go. So let's put that this is an electron, not a +1 charge. So the electron that you add is going to go into an s, and for here the electron that you add is going to go into a p. And surprisingly, this is very difficult. So magnesium and the other elements that are in that family cost a lot of energy to add an electron to those elements, whereas adding electrons to the family with sodium is not a high cost. You actually get energy out of it. It's actually a good thing to add electrons to sodium. And this last exception is related to one that we saw before with the ionization energies. So the group 15 versus group 16 electron configuration. Let's go ahead and take a closer look at that. All right, so here we have the electron configurations, or actually the orbital diagrams of nitrogen and oxygen. So nitrogen with its 7 electrons has a half-filled p orbital. It has 3 electrons in this 2p orbital, whereas oxygen has 4. And so we commented how this half-filled p orbital is a little bit extra stable, which is why the ionization energy of oxygen is lower when you would expect it to be higher, because it's easier to remove an electron and get to this favorable half-filled situation. And along the same vein, adding an electron to mess up this favorable half-filled situation is a little bit harder. So in general, you would expect the electron affinity to decrease going from nitrogen to oxygen because it increases going right to left on the periodic table. So you would expect a decrease in electron affinity. Instead, you see a slight increase. So since nitrogen has this favorable situation, adding an electron is not something it wants very much, and so it's slightly more difficult to add an electron to nitrogen than you would expect. And it is slightly easier to remove an electron from oxygen than you would expect. Let's take a look at the actual numbers, and you can see why they are a little bit tough to follow. So here is this chart from your textbook. You can see that, again, it's a little bit confusing because some of the numbers are positive, some are negative. In general, the electron affinity, the amount of energy change is increasing, going to the left and going down. So as far as increasing, going down the periodic table, the noble gases might be one of the better ones to look at. I mean, in general, from +20 to 35 to 40, it's getting more positive going down the periodic table. We do have this exception of neon. I really am not sure why that one is negative, but so we have a little bit of more positive going down the periodic table. If you look at the family for group 1, it's getting less negative going down the periodic table. So if you think about it, is it more difficult to get paid $72 or to get paid $48? I mean, it's more difficult to only get paid $48. Whereas over here, is it more difficult to pay $35 or pay $40? it's more difficult to pay 40. So in general, they're getting more difficult going down the periodic table, but again, you can see a lot of different families where this is not the case. So it's almost like the exceptions are easier to predict than the general trend. So let's take a look at those exceptions that we pointed out. We looked at sodium and magnesium. So adding an electron to the 3s orbital is pretty favorable. You get 53 kilojoules per mole out of that, whereas adding an electron to magnesium is extremely difficult. It costs 230 kilojoules to try to do that. We also had looked at the halogens versus the noble gases. Again, much more difficult to add an electron to argon. It costs 35 kilojoules per mole, whereas chlorine, you get 348 kilojoules per mole out of doing this highly favorable thing to chlorine. Giving it an electron is extremely good for it. We also mentioned nitrogen versus oxygen. So oxygen, adding an electron is fairly good. You get 141 kilojoules out of it. Nitrogen, you don't actually have to pay any kilojoules, but you don't get any out either. So this is definitely more difficult to add an electron than it would be to add one to oxygen. Let's take a look at the trends in atomic size, also called the radius. So it's probably not too surprising that as elements go down the periodic table and they get more and more shells of electrons around them, they get larger. So the size increases going down the periodic table. And you might expect that as the electrons build up going left to right that it gets bigger, but it actually is the opposite. It gets smaller going left to right because you're working on the same shell of electrons and the protons in the nucleus are pulling on that shell more and more, squeezing on it and shrinking it. So the size actually increases going right to left across the periodic table. So this is the general trend for uncharged atoms, regular elements, to get bigger going to the left and going down. Let's take a look at the chart in your textbook of the atomic radii. This chart is just plotting the size of the element just in order of atomic number. So starting with hydrogen, then helium, then lithium. So what we can see here, these elements in blue, helium, neon, argon, krypton, these are all the group 18 noble gases. And going down the periodic table, so helium is above neon, neon is right below that, argon is right below neon, krypton is right below argon. So going down the periodic table, you do see this definite increase in size. So the next noble gas is larger in size than the one above it. The same thing happens with this group 1. We have the alkali metals here, lithium, then sodium is bigger than lithium, potassium is bigger than sodium, and so on. Going down that column, you get a larger and larger size. Within a period, like say the third period, starting with sodium, going to magnesium, and then aluminum, silicon, all the way to argon, you do see a decrease in size. So left to right across the periodic table, you see a decrease in size. There's an increase going from right to left. It's definitely smoother in these main groups. Once you get into the transition metals, there's a little bit of a bumpiness here. But even in this fourth period, without the transition element dip and bump over here, if you just look at the main group elements, there is a decrease going across the periodic table for all of those dots. We are also going to look at the size of ions. So when you form a cation and lose electrons, you're going to get smaller than, an atom that is neutral and has all its electrons. And on the other hand, if you gain electrons and form an anion, that's going to make the atom larger. So I went ahead and summarized it with this sentence instead of like these three sentences. If you have two atoms that have the same number of protons, more electrons is going to make the atom bigger. So this might be a little bit easier to remember, whichever way is easier to remember. And then if you have atoms with the same number of electrons, so maybe you have one element that's neutral and another element that's a cation or an anion, but they have the same number of electrons and different number of protons, more protons is going to make that atom smaller because it's going to pull on that electrons harder, and the same electrons will be squeezed into a smaller size. So that is what this last sentence means, talking about things that are isoelectric, having the same number of electrons. Then if you have more protons and increasing nuclear charge, that's going to make the atom smaller. All right, so here, this first problem, we're comparing different ions and atoms, trying to see which one is larger. Magnesium versus sodium. On the periodic table, sodium is just to the left of magnesium. And so we know that going to the left is where the size increases, so sodium is going to be bigger than magnesium. Here we have two iron ions. They have the same number of protons, so more electrons is going to make this bigger, and iron with just 2 electrons missing has more electrons than iron with 3 electrons missing. Having an additional electron go missing is going to make it smaller, so this iron is going to be larger. So on the periodic table, gallium is right below aluminum, which would make it bigger than aluminum. So this is going to be larger. Here we have, again, atoms with the same number of protons. The anion chloride is going to have more electrons, and so that is going to be larger than the neutral chlorine atom. Here we have a potassium ion versus a neutral potassium atom. And so the neutral potassium atom is going to be larger. It has more electrons than the cation. And on the periodic table, bromine is to the right of selenium. That would make it a little bit smaller. Selenium should be larger. Okay, this next question we're looking at which of these would have the same number of electrons as a sulfur anion. So sulfur is atomic number 16. A sulfur anion would have 18 electrons. Let's take a look at the number of electrons in all of these. Aluminum is atom 13. A +3 charge would give it 10 electrons. Oxygen is atomic number 8. A -2 charge would give it 10 electrons. Calcium is atom 20, and a +2 charge would give it 18 electrons. So the answer is that calcium ion would have the same number of electrons. The next question is whether the calcium would be smaller or larger than the sulfur ion. Since calcium has 20 protons pulling on that electrons and sulfur only has 16 protons, this is going to be smaller. More protons would make it be smaller, so the calcium would be smaller. The calcium ion would be smaller than the sulfide ion. So the sulfide ion would be larger. Between these two, let's get a little bonus question going. These two are isoelectric because they have 10 electrons. So these ions are isoelectric with each other. Let's separate this, make a separate question out of it. So comparing these two ions, maybe pause and see which one you think would be bigger and which one would be smaller. Okay, hopefully you figured out that this one with more protons would be smaller, and the oxide ion with fewer protons would be larger. So the oxide ion would be larger than the aluminum ion.